When a star dies, most of its contents are scattered all over the place, but some of them stay in place due to strong gravity. What happens next depends on how heavy the remains are. If the star was relatively small, around the size of our Sun, it will shrink into a white dwarf, a small, dim, but a very dense star. If the star is much bigger, thousands or even million times bigger than our Sun, it will become a neutron star, or even a black hole. Neutron stars are very interesting. For example, they are so dense that 1 teaspoon of neutron star matter would weigh more than all people on the Earth combined. And black holes? They are even crazier than that. Let's take a look at them. We will first need some kind of a visualization. Let's stick to the Einstein's idea that gravity curves space-time. Don't worry, I will explain it to you. Because Earth is heavy, its gravity will curve the space like this. Now, when we place an object on this plane, it will fall towards the Earth, accelerating. If we give the object an orbital velocity, it will fall sideways so fast that it will never actually hit the Earth. It will orbit. Now that you understand this model, we can apply it to a black hole. The gravitational pull of a black hole is so incredible that not even light, the fastest thing in the universe, can escape it. There's this line that light cannot cross, the event horizon. And by the definition, we can't ever look past this limit, because information simply cannot cross the event horizon from the inner side. This implies that what happens in the black hole stays in the black hole. If you drop something into it, it's gone for good. Okay, that sounds scary. So should we be afraid of black holes? Well, not really, since black holes are pretty rare, and even the closest ones to the Earth are probably thousands of light years away. But we still might not be safe. Look, this is a quasar, a black hole that's actively feeding on matter. Around the quasar you can see a disk of matter that quickly orbits the black hole. In fact, so quickly that the rotation creates so much energy that this death ray of ionizing radiation, which is a type of radiation that can destroy our DNA, appears. If such a thing were to point at the Earth, we would all die pretty quickly. But again, the odds of this happening are very low. So, black holes get bigger and bigger and eventually consume everything in the universe? Well, fortunately no. Firstly, black holes don't work like vacuum cleaners. In fact, if a solar mass black hole were to replace the Sun, nothing would happen. We would still orbit it, because its gravitational pull would be exactly the same. And secondly, black holes actually lose mass over extreme periods of time due to Hawking radiation. Wait, how can they lose mass if nothing can escape them? That's a very good question. Scientists believe that in complete vacuum, pairs of so-called virtual particles randomly appear and annihilate themselves immediately. This could theoretically explain why the universe is expanding. If empty space has energy, it would make sense that it is expanding. But since we don't know much about this yet, let's stick to the Hawking radiation for now. When the virtual particle pair appears just on the event horizon, one particle stays in the black hole, but the other one suddenly can't disappear, since it has lost its partner. So it just floats away into space, stealing some energy from the black hole. This process is incredibly slow, as you can imagine, but it speeds up as the black hole gets smaller. There's this crazy idea that we could create a really small black hole, which is very hard but not completely impossible, and feed in matter to create the perfect power plant. Since black holes convert matter into energy with no losses, and we know from E equals mc squared that in every bit of matter there is a ton of energy, we could generate as much energy as our future galaxy colonizing generations would ever need.